All right. Hello, everyone. We'll go ahead and get started. Welcome to our seventh and final bioastronautics workshop series for this year's season. This series, hosted by Starlab Space and the Ohio State University Human Performance Collaborative, is intended to intersect academic and industry researchers within the space sciences and spark conversation about the big challenges and big opportunities that space exploration presents to us. Over the past year, we have explored topics such as microbiology and immunology in space, development of new technologies for space, medical advancements in space, and many more. Today, we have two leading experts with us, Dr. Emily Matala from NASA and Dr. Pablo de Leon from University of North Dakota, to discuss advancements in space operations, training, and spacesuits. So we will go ahead and we'll start with presentations from each of our speakers, and then we'll have an audience question and answer period at the end. So please save all of your questions for that period at the end. During the question and answer session, if you would like to ask a question, please feel free to raise your Zoom hand. And then when called upon, you can unmute yourself and ask your question. However, if you would prefer, you can also drop your question in the Zoom chat and I will ask it on your behalf. I am your moderator for today. My name is Abby Harrison and I'm the Starlab Research Lead, and I'm really grateful to have both of our speakers as well as so many fantastic research community members with us today. So thank you for joining. We have a great session ahead of us, and hopefully we'll have a really interactive and great question and answer period and discussion at the end as well. So without any further ado, we'll go ahead and turn the Zoom stage over to our first speaker, Dr. Emily Matula.
Abby,
Hey everybody, really quick. I'm sorry I had to move. I had somebody come into my office. We have a shared office, so thanks for your
Oh, no
patience.
worries. No worries at all. Thanks so much for still taking the time to join us today and present. So everyone just bear with us for a second while we get the transition worked over and Dr. Matula gets her presentation set up as well.
Thank you so much. There we go. All right, back in it. So, like Abby said, I'm Dr. Emily Matula. I'm down here in NASA Johnson Space Center in Houston, Texas, and I'm an EVA or extravehicular activity flight controller and instructor. And so, I want to talk a little bit about what that means to be an EVA instructor and how we use the spacesuit. So essentially, my path is pretty simple. I went from loving space to teaching space. So as part of that journey, it all started in Ohio, actually. So I grew up in Central Ohio in Granville, Ohio, which is about 30 minutes east of Columbus. And I always had a passion for space. And so this is a picture of me in fifth grade doing my science fair project where I was interested in the melting rate of comets. So I had different types of simulated dust. And by using the albedo and using a fake sun, I looked at the melting rate. And so I think from then on, my parents knew that I was going to somehow have some sort of a pathway to space. But as part of my journey, I went to the University of Michigan for my undergrad in mechanical engineering and my master's in space engineering. Then I went to the University of Colorado for my PhD in bioastronautics, where I was specifically looking at environmental control and life support systems, bioregenerative technologies, so looking at using algae for spacecraft air revitalization and thermal control. And that's what really cemented my passion in human spaceflight. And so after graduating, I came to Johnson Space Center to be the EVA flight controller and instructor. And over the past few years that I've been here, I've had some really cool opportunities to teach a couple different crew, the most recent being Crew 8, as well as some spacesuit experiences. So I've had some dives in the neutral buoyancy laboratory, or the NBL, where I've gotten to get inside the EMU, the extravehicular mobility unit, which is the big white spacesuit that everybody's familiar with. But I've also had some opportunities with some of our future suits, our XEMU, which is the government reference design, as well as the Axiom suit. So I've got some really cool insight of the mobility of all those suits as well. So really excited to share with you guys any of those experiences if you have any questions about those. So what does it mean to be an EVA instructor? Well, essentially you're turning astronauts, however they come to you, into EVA experts. And so this is Aki, and in his first day, we had to teach him how to put on his spacesuit, and then he was able to go on and successfully complete a few EVAs as part of his mission. But how do you become an EVA expert? Well, there's two main components. There's the suit side, so understanding the ISS EMU, that's the current suit that we're using on the International Space Station. So knowing how it works, really understanding your system, but also how to keep it clean, how to keep it functioning, and how to put it on. And then you have to know how to use it once you get out the door. So how do you actually execute a spacewalk? So how do you get ready to go outside? What types of tools are you using? How do you move around the station? And what happens if you come off of station? So as part of their first classes, because we have what's called a training flow that takes approximately a year and a half after they're assigned a mission, they will learn all the ins and outs of the spacesuit. So they learn all the different loops in the system, as we call them. So this is your primary oxygen loop, your secondary oxygen, cooling, your ventilation loop where you have CO2 scrubbing. And so they learn all about the different loops as well as some of the operational ranges of those loops. And so we empower them to understand their suit so that when they're going out the door and they see some off-nominal values, they can report those to us and they can be informed of maybe what's going on, because we don't always get all the data on the ground. And so we rely on our crew members to give us all the information that they can if something is to go wrong with their suit. So they learn about all the systems, they learn about all the pieces of the suit as well, and they also learn about all of the different components and systems inside the airlock. So we've got different pieces of equipment that are used to support getting ready for an EVA, as well as maintaining the suit and replenishing suit consumables. So they also get to learn about that. We also teach them how to keep the EMU clean. For some folks who are familiar with EVA 23, this was a breakdown of the water loop inside the EMU. And what I mean by that is we had contamination in the water that wasn't adequately cleaned out, and it ended up clogging our water separator, which in turn ended up redirecting water away from our water tanks and towards the helmet of the crew member, ultimately pooling water around their face and could have potentially drowned them. Since then, we have really stringent water contamination protocols and cleanliness standards, but we also have cleaning procedures and activities that we have on very strict cycles as well to help make sure that we keep those water loops as clean as possible and minimize contamination in that water separator. So one of the classes, or actually a few of the classes that the crew take, are how to use these different pieces of scrubbing equipment and what to look out for to make sure that your suit isn't contaminated. And then we have the fun part. How do you put on the EMU? So it's kind of like a shirt and pants. So we call this a suit, or we call this waist donning and doffing. So we take the lower torso off of the hard upper torso, and the crew members will then put on that lower torso assembly, or LTA, and then they will slip into the hard upper torso and then connect the two pieces together. And so how do you get ready for an EVA? It's actually like a 3 to 4 hour process. So I'll play this video. Time lapse is really cool because it shows everything going on. So the crew first start their pre-breathe, so 100% oxygen to replace the nitrogen in their bodies with oxygen because they're in a 100% oxygen environment, spacesuit. Um, and as they are breathing on that, you can see that they have their liquid cooling ventilation environment on. So that's cool when they're in the suit. Checks, contacts on, and then they actually get into the suit. So they've gotten into the suit, they hook up their biomed connector signal harness as part of their ECG, that's bodies, and close up the LTA, and caps, put gloves, put on the helmet, pressurize the suit, do the leak check, and then one of the last things they do is the IO protocol, which is where they do a little bit of exercise, again, to help work that nitrogen out of their bodies, replace it with oxygen in their tissues. After they're done with their IL pre-breathe, then the tool is attached to the suit, and then we swap out the Medox canisters, the CO2
Dr.
canister, and put on the
Matula,
back of the suit.
sorry, just a minute, gonna interrupt. We're having a really hard time hearing you. It's just
Oh,
coming in and out a little bit. Audio is maybe having a hard time, I think, playing at the same time that the video is playing. So I was
oh,
wondering,
sure.
oh, perfect. See, now that the video is done, I can actually hear you perfectly. I hate to ask this of you, but could you tell us the details of everything you just said during the video about that process?
Hey, sure, absolutely. Let me play the last 10 seconds and then I'll circle back and get all the information to you guys.
Perfect. Thank you so much.
Fabulous. All right. So sorry about that. What I was saying before was at first you saw the crew members with these masks on their faces. They were breathing 100% oxygen as part of their pre-breathe protocol. This is where we basically replace nitrogen in our tissues with oxygen because they are going to be going into a 100% oxygen environment in the spacesuit at an overall relatively lower pressure. So if folks are familiar with decompression sickness, there is a risk that if we didn't do this pre-breathe protocol, that by going into that 100% oxygen environment at the lower pressure, crew could potentially get bent. So the nitrogen that comes out, that is in their tissues, could come out of their tissues in that lower pressure environment and create the bends. So we do this pre-breathe protocol that replaces the nitrogen in their tissues with oxygen and helps prevent that risk of the bends. The spacesuit operates at 4.3 psi, and so it's a nice balance between providing enough oxygen to the crew member, but then also not making the spacesuit so rigid that they can't move around when they're doing their spacewalk. After you saw them with the mask on, you saw that they did some comm checks. You probably noticed also that they were in almost what looked like white onesie. That's their liquid cooling and ventilation garment. This is what we use to keep the crew members cool inside the spacesuit. So it's essentially a onesie that has a little plastic tubing sewn into that onesie, and cooling water flows across the crew member's body through that tubing system and then returns back to the suit for processing. So once the crew members are done with their comm checks, they get into the suit. They hook up their signal conditioner, which is attached to their sternal harness, which is an ECG system. And so that provides health monitoring for the surgeon down on the ground. Then we attach the LTA, the lower torso assembly. We put on the gloves, we put on the helmet, pressurize the suit, do a leak check. And then one of the last things we do is we do a Medox canister swap. So our Maddox canister is our CO2 scrubbing system. It's one of our limiting consumables when we're out EVA. So we swap out with a fresh one right before we go out the door. And then the final thing that you saw was putting on our SAFER, or our simplified aid for EVA rescue. We'll talk about that a little bit later, but it's essentially our jetpack that allows us to fly the crew member back to station if they come detached from station. Right. So some of the other things that we teach our crew members are the different types of tools that they'll be using while EVA. So you saw in that video, during their pre-brief protocol, they were attaching tools to the front of their suit. So they have a mini workstation. This is that T-bar that you see here, attaches to the front of their suit. And it's basically a small tool belt that allows them to hang tethers off themselves, as well as body restraint tools or tethers that allow them to grip onto station. We also have a pistol grip tool, which is kind of like a drill almost. So we have different speeds and torques that allow the crew members to drive bolts and remove bolts to either replace different pieces of hardware or to install different systems. And so we also got to give nod to Artemis, since we're going back to the moon. But we've been taking some lessons learned from Apollo and understanding how we're going to be using Apollo geology lessons to Artemis. So it's really cool. We are using some of the same areas in Arizona, New Mexico, Iceland that the Apollo crew used. So we've been taking some of those lessons learned. And so fast forward from the 50s and 60s to today. And so, like I said, we're taking a lot of those lessons learned. We're sending our astronauts out into the field. We're teaching them geology skills, but we're also doing it in mock-up suits that I think Dr. De Leon will talk about later. But it's giving our crew members an opportunity to better understand what it's going to be like for the Artemis missions. This is a really cool shot here. We were doing a geology test or a operations test, and we had a simultaneous picture taken. So the crew had an ISS flyover, and they were taking pictures down in our geology area, and we simultaneously were taking pictures of them. So really cool. And then for the station, we have the neutral buoyancy laboratory. So it is a 40-foot deep pool that has a 1-to-1 mock-up of the ISS submerged into the water. And so that's where we do all of our external training. So as a part of that, we do traverse training. So this was an NBL run that I did a few years ago. And you can see it's a lot like rock climbing. So we're looking for your handholds across station and everything, and making sure that you're picking the right spot and you're not hamstringing yourself by maybe getting into a situation where you don't have a handhold in front of you. And to stay still at a work site, you use an APFR, or an articulating portable foot restraint. But these are actually really, really tricky to learn how to use. So you have clips on the back of your boot in order to hold yourself in place. So you first kick your toe into the toe loops, as you see right here, and then you swivel your heel around so that it catches the lip in the back of the APFR. However, you can't look down at your feet. The suit just doesn't bend at the waist, and so it's really hard to see where your feet are. So you have to do it all by feel. And so that's what I was struggling with. You can see I'm holding onto a handhold, looking around at that APFR, trying to figure out how are my feet going to get in there. I was able to get 1 foot in. You can see my left foot was able to successfully slide into that heel clip, but my right foot, it was in the toe loop, but it was pushed in just a little too far to get into that heel clip. And so then I'm feeling around, trying to feel where that heel clip is. Okay, I think I've got it. And so I swiveled my heel around, and then it was able to drop into that heel clip. And I was able to push it back, swivel it around, and get it caught. I think that happens like right around here. And the thing is, it's really hard to do it the first couple of times, but after you get that motion and you understand the motion and body positioning, it gets significantly easier after that. But we have to use that in microgravity because Newton's laws work really well in microgravity. For lunar mobility, we used to have the vomit comet, so we could do partial gravity manipulations and traverses. But now we use the neutral buoyancy laboratory. We also have Argos, which is an offloading system, a dynamic offloading system that allows us to program different gravity settings. In this case, we do lunar gravity and allows the crew member to traverse around, and we can also do suit testing with it. This is a link. Let me see if it'll play. Here we go. So this was Xena in an exploration suit a few years ago, testing out the mobility of this new spacesuit, and it was really cool to see her go through and do some of the geology sampling and trying out the different tools and everything, and understanding, did she have better mobility? What did she feel like in the suit? And just to see her hopping around like the Apollo astronauts was really cool too. Right. So if you come off of station, what happens then? So we talked about SAFER a little bit, simplified aid for EVA rescue. And it is, like I said, that jetpack. So we have a hand controller that you will deploy and you would use to basically fly yourself back to station. And when I say jetpack and flying, we have essentially a pressurized canister of nitrogen inside of this backpack that's strapped onto the PLIS, the primary life support system. And depending on the inputs of the hand control module, there are 24 thrusters all around this SAFER, and they will basically puff out just a little bit of nitrogen to help stop the crew, stabilize the crew, and then direct them back to the station. Right. And so once the crew members complete all of their training as well as doing their testing in the MBL, then they can say that they are EVA experts. They're ready for spacewalks when we go to the ISS. All right. So I can take a couple questions now, or due to timing, we can move on to Dr. De Leon.
Yeah, thank you so much, Dr. Matula. That was really, really fantastic and so interactive. I loved seeing all of the visuals that you provided that really helped some of those ideas click. So thank you for sharing that. I do think we have time for maybe one or two questions for Dr. Matula before we move on. So if anyone has a question specifically about that presentation, please feel free to either put it in the chat or raise your Zoom hand. I do see one in the chat, which is from Serena Mathis. And Serena says, Dr. Matula, how should someone know if they have what it takes to be an astronaut? Which I think is really a fun question to ask someone who interacts so frequently with astronauts and crew members and helps with that training.
Yeah, that's a great question. I think it's a really hard thing to do a self-assessment. But what I would say is some of the characteristics that I've seen with a lot of our crew members are interpersonal skills. So being able to communicate effectively with all different types of people for a couple of different reasons. One, you are a representative of NASA as well as a space community. And you're also trying to encourage other people to be excited about space, to get them interested and to bring them into part of that space program, that space excitement, or moon joy. Um, Also, you're going to be working with a lot of different types of people. So you're going to be training with all different sorts of people. Um, and what I mean by that is your instructors come from all walks of life. And they have all different types of backgrounds. And so being able to communicate effectively with your trainers, get the best out of their instruction is super important. But then also, you're going to be spending a lot of time with crew members, possibly for upwards of 6 months in the International Space Station for, you know, basically being in a 3 bedroom apartment or smaller. And so understanding how to communicate effectively as well as work as a team is super important. And so what I would say is it can be really hard, like I said, to understand if you have what it takes. But if you have some of those characteristics like communication, interpersonal skills, and teamwork, I think you can hack it.
Thank you so much. What a great answer that it really revolves around teamwork and working collaboratively with each other. So another question that we have is from AJ Kumar, who wants to know what body parameters are measured during an EVA.
That is a great question. So during an EVA on the ISS, uh, we really only track heart rhythm and heart rate. We also will track metabolic rate, but not because we're interested in um, what what the metabolic output is for the crew member in terms of like fatigue, but we are more interested in how our CO2 scrubber system is doing and what the remaining capacity is for that CO2 scrubber system. So we'll measure the met rate, and then we will basically back calculate into what does that mean for our CO2 scrubbing system in our remaining EVA time. Before the crew member goes out on their spacewalk, we do fit checks. So crew will get into the spacesuit. Since they will have been on station for a little bit of time, their spine will have elongated, and even some of their peripheral, body parts have probably stretched out and expanded a little bit, and so it changes how you fit in the suit. So we do that fit check. We make adjustments, and then that also is something that body part, body parameters that are measured for an EVA.
Amazing, thank you. So we do have time for one more question, so I'll go ahead and grab one from the chat. But I did just want to mention if you put a question there and it hasn't been asked now, I'm recording them and I'll make sure that questions get asked during the end, during our larger Q&A period. So feel free to continue to drop questions either specifically for Dr. Matula or during Dr. De Leon's presentation as well, and we will revisit all of those. So our final question is, Dr. Matula, it's from Nikita Mikhailov. And Dr. Matula, what is your favorite part of your job?
Probably the teamwork aspect. So one of the fondest memories that I have looking back, actually, I've got two. One of them is getting calls from space from some of my crew members that I taught and trained, because they wanted some reassurance, some advice, things like that. And so it was a moment where I was like, wow, these people trust me. That's incredible to have the trust of people on the team, and what I say is going to matter on how they execute their EVA. So that was really special, and it really meant a lot. The other thing is I've had a couple of opportunities where we've had to basically rapidly develop some procedures in order to address some issues we were having with the spacesuit. And so it turned almost into like an Apollo 13 type style, like, all right, drop everything, throw all the data on the table. What are all the different components that we have? Let's build this procedure. Let's figure out how we can solve this problem. And we did it as a team, and I think that was the coolest part is everybody was bringing little pieces that they had of information as well as potential solutions, and we kind of Frankensteined this procedure together, and it ended up working in the end. But it was really cool to see this development of 0 to 100 within 24 hours.
That's amazing. Thank you so much for sharing your experiences with us, Dr. Matula, and for the fantastic presentation. So next up, we have Dr. De Leon. Dr. De Leon, would you mind sharing your screen and go ahead and start
Sure.
your presentation?
Sure. Let me see if I can remember how to do it again. Hello, everybody. My name is Pablo de Leon. I'm a professor at the University of North Dakota in the Department of Space Studies, and I'm the current chair, which I hope very soon to go back to being a professor, a researcher, because clearly the bureaucratic work associated with being a chair is not my thing. I have been doing it 6 years already, and I'm looking forward to go back to being a full researcher. Um, I think right now it should be okay, full screen, right? Just to double check that this is the case.
Yes, it looks
Yeah.
perfect.
Good, excellent. So, very briefly, let me uh, tell you a little bit about my history here. Um, I'm also, as Dr. Matula, extremely passionate about space, but I belong to a way older generation, the old folks generation who grew up in the 60s. So I'm what we call ourselves the children of Apollo. I was someone that while I was being a kid, I was able to witness the Apollo missions to the moon and watching, with my own eyes as Neil Armstrong was stepping on our natural satellite. And since that time, I became fascinated with space and the possibilities of space exploration, particularly human space exploration. So everything I wanted to do in my life was something related with space. And by my accent, you can tell I'm not from North Dakota. I'm originally from Argentina. So it was a long story of how I ended up in the United States. I worked at the Kennedy Space Center for a number of years in the 90s. I worked with space shuttle payloads. Um, and then in 2004, I accepted this job at the University of North Dakota that was basically to try to develop the portion of human spaceflight at the university. The University of North Dakota is also a state university, as Ohio State. And on that page, let me tell you a very brief story regarding my visit to Ohio State a couple of years ago when the NASA-sponsored deep space food competition was taking place. I was in one of the teams, so I had the opportunities to spend part of the summer in Columbus. So I got familiar with Brutus, Buckeye, and all the things about OSU, and I enjoyed that university a lot. It was a very interesting experience for me, and knowing that now the university is involved with Starlab, um, and we at the University of North Dakota, as another state university, are there to help in any way possible and make Starlab a reality. So with that, let me briefly mention. The Department of Space Studies at the University of North Dakota is a graduate program, so we have masters and PhD in aerospace sciences, and I'm going to show you specifically what we do in the Human Spaceflight Laboratory, which is one of the labs that I direct. We started in 2004 with the design of what was our first experimental suit. This was sponsored by NASA and was our first surface suit or planetary suit. One of the things different on these surface suits, as opposed to the EMU that Dr. Matula was explaining, that is basically a microgravity suit that hasn't been optimized to for walking, because in microgravity you don't have to walk any place. In fact, it's better that you are stable on the foot restraint, so you can do things with your hands while your legs remain as immobile as possible. The intention in our lab was to specialize in lower torso mobility, trying to design the joints that are necessary to be able to, to walk on another planetary body, moon or Mars. So that's what we did through the years, and I will go very quickly through a number of images
on different designs that we went through the years. This one, which we affectionately call it our tiger suit, it was our first experimental suit that was a high mobility Mars suit that we developed and again under a research grant from NASA. And this was a basically a suit where we study the kinematics on reduced gravity gradients like lunar Mars. Specifically, this suit was for Mars, and it's mainly a soft suit, a suit made out of different fabrics with a carbon fiber upper torso in a kind of a similar fashion of the EMU for the ones who are familiar with that one. So this is briefly about our lab, what we do. We created in 2005, and we have been working on it for the last 20 years, initially funded by North Dakota Space Grant Consortium and NASA as well. So these are just some pictures of our suits. We work with different NASA centers. Johnson, uh, Kennedy, Ames are the ones that I remember. This picture, for example, is in the Mars tunnel, the Mars WIT at Ames, where we did a dust study on using Mars regolith simulant, of course. Um, we took also under Ames grants our suits to Antarctica to do sample collection to try to study how much contamination we bring from our suits and from the humans that are manipulating the suit into a Mars sample. This is in Australia, where we did studies on stromatolites. So we have been using our suits a lot as kind of NASA tools to do different studies in the field. All right. We have also at the UND University of North Dakota, a number of spacecraft simulators that were built by our grad students as well. This is one for the Spaceship One. This is our second suit, which is the NDX-2, which is a lunar suit prototype. This one is a rear entry suit, similar to the XCMU and the Axiom suit. We are using this one as for testing because now we built our own reduced uh, not reduced gravity, but gravity offload system. So we are able to simulate some of the walking characteristics on the moon or Mars. So this is kind of similar of what is available at NASA as well, but ours is in a way smaller scale. Um, the Argos is the one that I was referring to at NASA. So these are some of the pictures of the NDX two pressurized, and what you are seeing is a restraint layer. The suits are normally covered by what is called the TMG, a thermal and micrometeoroid a garment that goes on top of what you are seeing. What you are seeing is kind of part of the interior of a suit. These are just some of the joints that you can adjust. And this is in the lunar regolith. We do a lot of work with Kennedy, specifically Kennedy Space Center, specifically with SWAMWorks. So these are some of the tests that we are doing in their lunar regolith beam. Okay. In fact, we do have a lab at the Kennedy Space Center, a UND lab. And this is another picture of that lunar regolith beam when we were testing the NDX-1 suit. As part of other collaborations we do with NASA and specifically with Kennedy Space Center, we participated in a materials exposure experiment called MISS, which is Materials in Space, I think it is, the mission number 11, where we expose a number of spacesuit fabrics 1 year into the environment near the International Space Station. And this lab that I was telling all you about, we conduct a number of different tests in there. Let me go back to our campus in Grand Forks, North Dakota. And as I mentioned previously, I have been at UND for 22, I was going to say years, but in North Dakota we count the winters instead of the years, so it's 22 winters. As part of my work at UND, we put together this project under two different NASA grants, called it the Integrated Lunar Mars Habitat, the ILMA. And this is an analog facility where we simulate a lunar base or eventually a Mars base. The conditions in North Dakota in the winter are extremely harsh, as you can imagine, with temperatures in the order of minus 50 uh, Celsius or Fahrenheit, whatever you like, because at that temperature we are pretty close. This habitat was built is a multiple modules. Some of them are inflatable, like this one here, which is our core module, the living quarters, and some others are rigid, just like the ones in the International Space Station. We also have a pressurized rover that Dr. Matula was mentioning, the one that they have at JSC, which is way nicer than an ours, and the one that will be built by JAXA very soon. We have also our rover, which is a converted electric cart with the two suit ports in the back, so we can detach the spacesuits from the back of the rover, and the test subjects can do their research outside, performing EVAs with ventilated suits. They are inflated, but they are not at 4.3 psi. They are way lower, it's just 1 psi. But we can simulate entire EVAs, surface EVAs, that is. This is where when we were building our habitat, putting it together, when doing the insulation. Again, as you can imagine, on North Dakota, because of the temperature, you need to properly insulate this. Of course, it's not the moon, but it's pretty cold. And we have been doing a number of analog missions through the years. With normally 4 crew members. This is from the time that we had just one module, where we perform missions up to 30 days. Can you imagine? This is a pretty small living space for 30 days. And these are some pictures of in the inside of the lab. This is during the 30-day mission. We did a lot of research with plants as well, and in the last few years, through a second NASA grant, we were able to incorporate 4 additional research modules to our habitat. So right now it's way bigger, and I'm going to be passing some of these pictures, so you can see some of the activities inside the habitat, etc. This is the plants production module, which is one of these 4 modules that we built a few years ago. The test subjects only leave during a mission in their suits, and this is a planned operation where you have communications with them. Sometimes you have biomedical systems, etc. They perform inspections and repairs outside. They have an airlock that they have to go through in order to simulate that you depressurize that section in order to go outside. We built the plant production module with the help of the Kennedy Space Center, where they do a lot of plants research, and we concentrate on edible plants. What we produce inside the plants production module is just things that you can eat during a mission. Up to one point, we were able to produce 30% of the food consumed in the ILMA in this module. And as I mentioned, as part of these 4 modules, one is the plants production. We added geology, science, and exercise modules. Later, you can see some of them. They are all connected together through tunnels, so the crew members can go from one to the other. And this we perform night EVAs as well. And let me see if this video we can make it work. This is a collaboration we did the University of Hawaii on the design of a robotic system for the maintenance of the plants. Through an AI power system, they could determine with a camera if any of the plants had any sickness, and cut the portion and transfer it. It was a very interesting project that we did just a few years ago in our lab as a kind of a demo of a collaboration between universities. Um, Anyways, let me just continue here. So, oops, let me go back. So, this is what we have now. Here you can see this is the core module, which are the living quarters. These are the sleeping quarters for the crew members, hygiene facilities, kitchen, and a small lab area. And interconnected to that are these four modules that you can see here. This is the exercise, this is a lab, this is the EVA module with the airlock, and this is the plants module. And through this tunnel, you can leave to the pressurized rover that we connect through a retractable tunnel. So this is when we were building the modules. We built everything locally with our students, getting a lot of hands-on experience. So it was a fun process. This is when we were moving it to the field, and this is again in the winter. By the way, this is me right here with my vehicle piloting a rover to take this picture. And you can tell during those temperatures, you normally can stay just a few minutes outside, and the batteries of your drone just will go to zero in minutes. So you have to learn how to really work in these conditions, right? Sometimes when you talk about Artemis and the lunar South Pole, you say, wow, this is going to take a lot of ingenuity to be able to work in these extremely cold temperatures, which are like at least 3 times colder than what we have in North Dakota. So some lessons learned. Another grant that I have been working recently is this one, which is try to use 3D printing technologies, printing flexible plastics, using flexible elements to build a spacesuit. So instead of using the traditional techniques of sewing with the typical sewing machine and gluing the parts of the bladder of your suit, just having a 3D printer system to put them together. So we have been working with that for the last few years with very interesting results. Again, this was through another NASA grant where we built all the different parts and we tested the suit under 4.3 or 5 psi, and we were able to obtain similar torques than the ones that you get on a traditional suit. So it's still a long way to go, but you can imagine that potentially in the future, this can be a way to reduce the dependency from Earth. You may be able to print your suit in destination or the parts of your suit on the moon or Mars. So it's a pretty interesting project that we're working with. So we got a patent from the U.S. Patent Trademark Office through this, and these are just some of the pictures of the one of the prototypes of the suit that is using rigid and flexible parts. There's still a lot of work to do, but some of the things that we're doing involves also mobility on the moon, on enclosed and open rovers. So, and this is what I was mentioning before. I tried to get a video to show you how our gravity offload system works, but I couldn't find one that is short enough to show it here. But this is a very interesting system. We're able to simulate lunar or Mars gravity and incorporate that with our suits. So it's not as fancy as the one at Johnson Space Center, but it works for the kind of study that we are doing at the university. And that's it. Thanks for my attention. And I made it in 18 minutes, 57 seconds. So I still have 1 minute to go. Thank you.
Thank you so much, Dr. De Leon. And you were under time. Fantastic. Thank you. Such an incredible presentation. It looks like UND has some, incredible history with all the research you've done. And I would maybe kick off by asking the first question then of what do you see as the most exciting next steps for UND space research in the next 5 or maybe 10 years? Ideally, where would you like to see the program go?
Well, let me mention something. I have been fighting for this for more than 10 years, and finally, by the summer of 2027, we'll have our own neutral buoyancy lab. Of course, it's smaller. We're talking about 8 meters by 8 meters by 8 meters. but we'll be able to perform underwater operations with our suits and other suits as well. So while is I don't know how many dozens or probably hundreds of times smaller than the Sonny Carter facility in Houston, we'll be able to do small EVA operations and test equipment and test systems in a controlled environment underwater. So we're looking forward to that. We will open that opportunity to other universities as well and other research centers. So we hope that that is going to increase our capabilities to support Artemis and beyond on EVA activities.
That is very exciting. Congratulations on that. What an incredible piece of infrastructure to be able to bring to campus and
Mhm.
be able to share with the broader research community as well. Hopefully, there will be lots of collaborative opportunities from people potentially even in this workshop today.
Mhm.
Um, so I another question that we have from our chat for Dr. De Leon is from George Pantelos who would like to know if parabolic flight capabilities return to the United States, are you interested in testing the new lunar suits that you've been developing during the 1/6 G portion of a parabolic flight?
Absolutely, absolutely. Many years ago, I was fortunate to do 80 parabolas in the KC-135 from Ellington Field. So I see the great value of having firsthand experience on that. So it's too bad that the ways to be able to perform research in parabolic flights nowadays is a little bit more complex because we don't have the NASA planes anymore. But absolutely, yes, I think that will be extremely valuable. And if you look at the history during Gemini and Apollo and beyond, the value of if you allow me to see the word the vomit comet is not is extremely important, and the value for training is I will say of a paramount importance. So certainly yes.
That's fantastic to hear. And I had the opportunity to do my first research parabolic flight about a year ago, and found that exactly what you just said there, that the value of those can't be understated, that you think you know how things are going to work. And then once you're in that microgravity
Mhm.
environment, it's like everything is quite literally flipped upside down, and it's just a completely different environment to be operating in.
Mhm.
So I think that
Yes.
that's really great to hear.
Yeah. Mhm.
Hopefully, we'll get those suits in some parabolic flights in the future.
Oh yes.
So another question from our community today is from Abraham Weaver, who says there's definitely a lot of science and engineering put into spacesuits, but how much computer science is worked into the suit itself? Are the health monitoring systems also made to work in parallel with the data analysis programs? And if so, how does that data contribute to improving the suit? I would actually direct that question to both Dr. De Leon and Dr. Matula, as I think it would be interesting to hear about the suits being developed for the future and the suits being utilized currently at NASA. But Dr. De
Mhm.
Leon, would you mind starting us off?
Sure. How can I put this nicely? A spacesuit is already an extremely complex machine. So my philosophy is not to make them any more complex that they need to be. I hear every single year, I have lots of students and even people from outside contractors or NASA that says, "Oh, let's put this thing; it will be super cool, etc., etc." And sometimes doing that, you overcomplicate the system and you turn it into more fragile than it should be, just because of the addition of multiple layers of of sometimes unnecessary complication. So, of course, biomedical systems, you have to have what you have to have. You have to have oxygen, CO2, you have to have temperature, you have to have heart rate, you have to have respiration, a number of things. However, sometimes I see a lot of ideas that are probably unnecessary, and they increase in the complexity to a point that makes them, and every single time that we do a test with those things, every single time what fails is these systems instead of the spacesuit. So I'm kind of just make something reliable, something there is a reason why nowadays you still see a 4A automobile that was designed in the 1910s, and still you occasionally see them running. And you won't see any of the cars of today running. And this is based on the number of parts. So I like something that is simple, that is reliable, that it works, and you can trust your life with, instead of something that has so many variables and sensors and little things that can go wrong, that you turn it into a more prone to failure that it needs to be. But in any case, that's my personal stance on this.
Yeah, no, that's really interesting. And I agree, don't over-engineer or over-design what doesn't need to be over-designed. Do you think that there's any concern there for future potential integration of computer design or computer sciences into spacesuit design, of the susceptibility of computer systems specifically to radiation?
W- w- uh, Yes, and I don't know much about the topic, so I don't know how you can protect the suits themselves and radiation. You don't get a lot of protection on a spacesuit from radiation. That's a field that we still need to, as we venture into deep space and we think about Mars. Certainly, radiation is probably the most critical issue that we are going to find to keep the astronauts safe while they are in transit between the Earth and Mars, for example, right? The moon is 3, 4 days away. Most of the times it's manageable, but when you are going to Mars, there is nothing that will basically protect you other than if you surround your spacecraft with water tanks or whatever. So I think in that field there is potential for improvement. Electrostatic shielding, or there are a bunch of things. I don't know if specifically it's computers, but um, yes, I think there are a lot of things. Being a science fiction fan myself, I always think about 2001 Space Odyssey and HAL 9000 going crazy in space. So I tried always to have a switch that you can turn everything off and rely on human interaction.
Right, in the AI age, it's more and more important to remember the lessons we've learned from science fiction.
Mhm.
Absolutely. Thank you so much for those thoughts. Dr. Matula, would you like to comment on integration of computer science into spacesuit design and development, or the potential capability for health monitoring systems and integrated sensors to be a part of, or maybe not a part of, future spacesuit designs?
Absolutely. No, I think Dr. De Leon hit the nail on the head, which is the EMU is actually almost purely mechanical in terms of how the valves work. The sensors are electronic, but they aren't actively um, regulating anything. We have purely mechanical regulators for the flow of the different systems, and so I agree. There's some simplicity with it, and there's reliability. And so when you are literally putting your life on the line and relying on the spacesuit, you want to make sure that that reliability is there. We are looking at integrating sensor-driven solenoids in their spacesuits with our future designs. And it's being met with mixed emotions from a lot of the community. You have people who think that this is great because it has a higher level of fidelity in terms of how you're controlling your flow rates and how that could potentially increase your EVA time. But then you also have people like myself that have seen different electronic components fail, and you want to make sure that they fail in a safe manner. And so that's something that we're currently looking at with some of our designs: is how do these things fail, and when they fail, are we able to ensure that the crew member stays safe and is able to get back to the vehicle and back to safe resources.
Agreed. And that's what it comes down to in the long run, right? Is building the systems that will best support the people who we're going to be operating within them. Speaking of building these systems, for any of our community members who are here with us today, both Dr. De Leon and Dr. Matula, what fields would you recommend that, for example, early career individuals, students, or those just starting out could focus on if they want to be involved in spacesuit operations in the future?
I don't know who should go first. Dr. Matula, please go ahead.
I, I was standing by and waiting for Dr. Dahlia. um, so if you're interested in spacesuit design versus the operations, um, I would say probably mechanical engineering, material science, engineering are all great things to focus on, as well as biomedical. So understanding how the body works, how the body is going to interact with these different components, I think are all super important. In terms of a mechanical engineer, you'll understand the different fluid systems that are necessary. So your ventilation loop, your oxygen provision system, as well as your liquid cooling. But there's also space for other people in spacesuit design. So it doesn't have to be like the standard engineering. It could also be electrical engineering because we still need sensors. We still need data to come from our suits. We still need radios. We still need interaction with our display and control modules with the crew members. And so even computer science. I know that we didn't really give the most hopeful outlook to people who are interested in having electronic solenoids integrated into the suit. But again, we're still going to need those sensors and those feedback systems in order to give us data. So I think there's still space for computer science engineers there as well, just maybe not in the sensor actuation mode.
Um, Let me see if I can explain this clearly. Um, because I have been involved in one way or the other as an spectator or as a professional working in the field for the last 50 years, and that's 50. That's a lot of time. Um, and most of this time, there were just one way of going into space. For example, the space shuttle, and nothing else. You either go with NASA, government-owned space vehicle, or you don't go at all. And what I see now is that we are entering into a completely different era. We are already on it, where you have a variety of vehicles, companies, destinations. I call it kind of like a new renaissance of space activities, which I never saw before anything like this. In the 60s, it was just going to the moon, but that was pretty much it. Now you have a lot of different things. So the number of opportunities are so multiple that I never saw anything like this. Never. And the interesting thing about space is that um, every single field of human knowledge needs to be represented in space in one way or the other. We're going to need space psychologists. We are going to need dentists. We are going to need architects. We are going to need electrical and material science engineers and chemistry people and doctors and everything. So because we are taking a portion of our planet with us. So we will need every branch of human knowledge in order to become multiplanetary. So I can't think right now any particular discipline that won't be needed in space. Animal herding, probably that may be one, but there are opportunities for everybody. And I have been talking with people who have the most crazy ideas, and they are coming with an idea to do root canals in zero G, or people and really, if you think about it, we'll need to solve it one way or the other. So it's a remarkable time for anyone who have a passion for space to be able to contribute to this effort that will go way beyond anything that we have seen so far.
Thank you so much, Dr. De Leon. That's a really beautiful and optimistic perspective and way to look at it. And I can't agree more with both what you've said and what Dr. Matula has said as well, that we are going to space as all of humanity, and we need all of humanity and all of our unique talents and capabilities involved. One quick follow-up on that before we jump back into some more technical questions about spacesuits and spacesuit training. We did have another question in the chat that Dr. Matul already answered, but I was hoping we could get it answered verbally as well, because it was such a fantastic continuation of this, which was from James Abney asking, how can a communications professional get involved with this? Dr. Matula, would you mind sharing what your thoughts that you wrote in the chat were with everyone?
Sure, absolutely. So, like Dr. DeLeon was saying before, there's a space for for everybody in space, and so one thing that we are really, I don't want to say struggling, but it can be a challenge for us here at NASA, is bringing the general public in and getting them excited about the different things that we're working on. And I think we're getting a little bit better, but we're still not as good as we could be. I think with Artemis 2, there was definitely a social media boom with getting people involved and excited, and letting people kind of into NASA and seeing what we've been working on. But it's a very small part of what we're working on. And so I think there's an opportunity to bring these communication majors, business people as well, so business majors, as well as marketing, to come in and help us understand how do we sell ourselves, so that we can get the public involved and get them excited. Because, not to make it all self-serving, but when the general public gets excited, then it gets Congress excited, and it brings more funding to NASA and allows us to do more cool things. So we really do need the help of everybody to get the general public behind us and keep us moving forward. In terms of like literally what do I do in order to get involved? So there's some really cool programs out there. So there is I'm going to have to look this up and I'll have to put it in the chat, but I believe it's the NASA Solar System Ambassador. But there's an ambassador program where basically if you show your passion for space and how you want to use your different platforms to promote space, you can become essentially an official ambassador of NASA to get people excited. So I think that's a really good opportunity. Plus, it encourages folks to go out, do outreach. So that's one way. Another way, again, I'm going to have to look this up. I'm going to have to put it in the chat. But there are other ways, either by using handles on Instagram and Facebook, doing posts and things like that, where you can get involved. You can also reach out to people who do podcasting for different space topics and understand, how are they doing what they're doing? And so there are a lot of people that are excited to share. And so reaching out to either podcasters or presenters that are presenting and understanding how they're getting these opportunities. But I'll put the links that I have in the chat. That way people can reference them.
Thank you, Dr. Matula. One more that I would add on to that as well, that I think is a great opportunity for people who are passionate about communications and about, science communication with the public to become directly involved with these NASA missions, is something called the NASA Socials, which is opportunities where NASA actually invites groups of people to basically behind the scenes opportunities. Sometimes it's like meet and greets with astronauts or tours of different space facilities at NASA in advance of important missions and launches. And I think that a lot of times when those applications open up, there's this assumption that's made that that's only for like the big creators and the influencers. And I want to put a quash on that and say that's absolutely not true. That I've seen people with, as few as like 100 followers or whatnot, like just local community engaged people be selected for those NASA socials. And I think that the intent there is not to only reach, the really big channels, but to have diversity in the people that are being engaged and the different local communities that we're involving there. So definitely, if you see those go live, they go live before pretty much every NASA mission. Put in an application, and it could be a great opportunity. Okay, so we have another really great question, which I think is really fun because it, it's kind of shows that for many of us, we're thinking big about where spacesuits could go in the future. Caleb Maher is wondering, for spacesuits, would they be designed for specific planets and environments, or are they built to withstand a more general threshold of environmental conditions? Dr. De Leon, would you like to start us off?
Well, I, I would say that perhaps we are not yet smart enough to build a suit that will work in every single environment. The environment, for example, on Mars and the Moon is so different, mainly because of the regolith characteristics, that I'll say that a lunar suit is way more challenging than what a Mars suit is going to be. On the Mars suit, you have different thermal scenario that we'll have to think it over. But it seems like while we never had contact with Mars regolith yet, it seems that because of the erosion process that Mars went through, it will be more benign to the different layers of the suits, of the fabrics of the suit, that what we found on the Moon. The Moon, because the absence of atmosphere and erosion in water, if when you examine the fabrics of the suits from Apollo that only spent a few hours or at the most couple of days on EVAs on the Moon, the regolith went through the layers of the TMG, and you can just imagine what's going to happen with suits that will have to operate on the Moon for months, years. So it's really challenging will be really challenging for the lunar suits to operate in that scenario. So right now, no, I guess we have to build suits for different environments. During Apollo, however, they did a suit that was an intravehicular suit that you can use for launch and entry. That same suit could be used with an umbilical to do an EVA in microgravity. The astronauts in Apollo, they used that to retrieve cameras or to retrieve experiments from outside the Apollo spacecraft while they were in transit. And they were also used on the Moon surface. But my suspicion is that for a while we'll need suits that are specific to each particular scenario. Now we're going back to the Moon. Those will be lunar suits. For Mars, we'll have to come up with something different because there is no way we can carry that mass that I can't remember, but say it's 150 kilos. So on Mars, it will still be 50 kilograms. That's a lot for many astronauts. So we'll have to get smarter building suits that will be lightweight enough so we'll be able to carry them on Mars for long periods of time. But that's my opinion, anyways.
Sorry, I was muted. I have to do it at least once on every one of these. It's tradition. But I was going to say, Dr. De Leon, that I really like that you started out in that response with, we're not smart enough yet to build a universal.
Hmm.
Maybe someday we will be able to.
Yes. Hmm.
But right
Yes.
now we build them for the individual environments. Thank you so much.
Mhm.
And then, I'm really curious to hear, and I think this would be directed for Dr. Matula. For astronauts, our Artemis astronauts returning to the moon, how will we communicate with them during EVAs? And is there any concern about the time delay that could have, or is that more of a concern that we keep in mind for future Mars missions for EVA operations support?
So it's interesting. We are at a crossroads right now. and it's a really exciting one. And we have a little bit of insight based off of how we did Apollo missions. But what I think we're realizing, especially living in this ISS world, is we can't do EVAs the way that we've been doing EVAs for the past 20 some odd years. Because we've been in relatively constant communication with minimal lag time in those communications. And so it's like having a conversation with your crew member when they're at the door. We're not going to have that, like you were alluding to. We're going to have upwards of a 7-second delay. And so it's going to be awkward if we approach our communications the same way. So what we're doing now is we're kind of migrating more towards a EVA crew driven conversation. So they know what they need to provide us in terms of our science objectives. So we're just basically going to let them go. We're going to communicate with them to, hey, can you go to this certain area? But it's going to be up to them to basically make all their observations, call things down, and then at certain points, basically pause, let us give them feedback of, hey, select this area or select that area, select this rock, maybe sample this area. But for the most part, it's going to be on their own. And so as we go further and further from Earth, we're starting to take that more independent stance. And so we've talked a little bit about Martian EVAs, but just kind of in the, hey, wouldn't it be cool? But I think what we're realizing is we're going to have to be pretty independent in those operations. And so the crew are, again, they're going to have insight from the ground of, what are the objectives and what are the things that we want them to accomplish in their EVA. But by and large, we're just going to have to trust the crew, which is funny because sometimes I think we have trust issues being ISS operators because we can watch them. We have cameras in the airlock and in the ISS. And so we will very commonly call up to them and say, hey, we're looking over your shoulder and we see that you may have missed step 18 in your procedure. And it can be kind of annoying for the crew, helpful, but also at the same time, like, guys, trust me, I got this.
That's so funny. I was just at NASA Glenn Research Center yesterday, working with some folks there on some flight flown hardware that we're bringing to OSU to support our education and development initiatives in space studies here. And one of the pieces that I found in one of the bins was a pipette that had been super glued to only allow pipetting of one quantity. And I asked one of the folks there, I was like, oh gosh, like what's going on with this? And they said, oh, that's astronaut proofed. That's to make sure that that there are no deviations from what the protocol was listed as, that they can only access this one quantity of fluid to pull up. So I think that's, it's gonna, like you said, it's gonna require that we make a change in how we conduct these operations. And it's exciting to be at that precipice of having the opportunity to do things in a different way and to explore in a way we haven't done before. So this does lead into an interesting question from one of our attendees in our chat, which is coming back to this idea of making high-tech spacesuits, which I know we've talked about previously, but Alexander Aun is interested in whether there have been any discussions that either of you are aware about integrating artificial reality or augmented reality, HUD, into spacesuit helmets. And he specifically is wondering, could a helmet-based AR display help astronauts by providing key information, procedural prompts, suit data, navigation cues, or other mission critical information during certain situations? Dr. Matula, would you like to start? Since we've just talked about the
Yeah.
specific instances of lunar EVAs that might have to change in the future.
Yeah. So I'll just make it brief so that Dr. De Leon can expound upon it. But yes, we are. We're thinking about it. We're looking at it. We're researching it. We're trying to figure it out. Right now, we have a system called Jarvis that literally is looking at trying to display either directions or pieces of suit data or caution and warning type messages on the helmet bubble. So yes, we are definitely looking at it. It's in the future, but it's not currently in the scope of integration for Artemis spacesuits, but we are definitely trying to get there.
Interesting. Hey, the future has to come at some point, right? Yeah. Dr. De Leon, would you like to comment?
Yes, we did several studies. I think like 3 years ago with the HoloLens and integration for augmented reality in one of our suits. In fact, the student who did that with me, she now works as a trainer at JSC. Um, but my question was always when the amount of situational awareness information that you get is way too much, and you get distracted by all these many cues that you're getting instead of concentrating in what you're supposed to do. So I think the fine line, there is a fine line between the information that you need and when it's way too much and it distracts you from what you are supposed to be doing, which is a critical task in a very dangerous environment, and just getting, of course, you want to know how much oxygen you have left, how much batteries, how all the system is working, but we have to be careful to determine when you are giving to the astronaut way too many reasons to get distracted and to fail in an extremely important task that he or she is doing. So that's my thought.
Yeah, that's really interesting. That's a great perspective to have and to think about that fatigue that can occur, mental fatigue, and especially as we look at what is probably going to be very long and arduous days for Artemis astronauts who have a lot of responsibilities on their plate. Living on the moon, not easy. So we have to be careful not to over fatigue. If anyone is interested in learning more about psychology in space, and questions like mental fatigue for astronauts. We did actually host a bioastronautics workshop series that was focused on that specific topic of space psychology, and it will be available on our Human Performance Collaborative YouTube page once that is posted. So you all get an email message about that. And I definitely recommend taking a look because it was some really interesting conversation. And I think anytime that we talk about human performance related or operations training, there has to be that conversation about the psychological realities as well, of humans, right? Because we're not robots and we're all unique individuals. Um, so I would love to ask a question to both Dr. De Leon and Dr. Matula. Something I've noticed with both of you is that you both have experience, and operational experience within Antarctica. So I'm curious to hear from your perspectives, how much value do you think there is in testing and evaluating extravehicular activity suits in those remote environments on Earth? Or are there better, less expensive, or more accessible ways that we can test them in the Earth environment? Dr. De Leon, we'll start with you because I know that you actually included a picture of yourself working with a suit in Antarctica. I kind of ambushed Dr. Matula about that because I just happen to know that, she's got a considerable amount of experience in Antarctica.
Well, Antarctica is like a reality check because you're just a few thousands away from any other continent, and you realize your logistic chain how fragile that is. Because if something fails or something goes wrong, and then you translate that to what it will be the moon or beyond, right? So first, the experience of Antarctica is something that is difficult to describe. Dr. Matula can I'm pretty sure she will have similar thoughts on that. Um, because really, chances are that you're walking on places when you're exploring and doing just your walks on Antarctica, you're walking on places that no human had stepped foot before. So I see a lot of similarities with space exploration there. I think it's an extremely valid environment to do simulation. And again, you realize how complex is if something goes wrong, something medical happens. So I think that the experience of Antarctic bases in general can be fully translated. In fact, there are books about there are a specific book that I remember that I think is called From Polar Exploration to Space Exploration or something like that. We can there are a lot of lessons learned that we'll need for planetary settlements. We'll need to take into consideration. So, to me personally, it was an incredible experience that I'll never forget. But yeah.
Thank you. Dr. Matula?
Yeah, I concur. So I have been to Antarctica two different times. The first time I was a grantee and I was in the dry valleys collecting algae. And I would echo what Dr. De Leon said, which is basically you are in an area where you put your foot down and it may be the first time somebody has ever put their foot down there. And it's really exciting, but it's also terrifying because you have this awareness of you're actively changing the landscape. And so you become very mindful of your activities and where you're going and what you're doing. But what's interesting too is you're in this environment where it literally is trying to kill you the entire time. And it reminds you that you're not supposed to be there. And not only is the environment reminding you that, but also your preparations as you go out and do your day to day job. So the second time that I went down there, most recently, I was there from this past October to February, a couple months ago. I was a coordinator at the long duration balloon facility where we would go out every single day in the middle of the ice shelf, which is about 12 miles outside of McMurdo Station. And every single day you had to pack your extreme cold weather gear bag. So it's a bag basically preparing you for your worst day. So if you got stranded out at the ice shelf, your car breaks or your van breaks down, or the truck breaks down, or there's a blizzard, a condition one storm that comes up, this is the bag that's going to keep you alive and keep you going for the next couple of days until either somebody can rescue you or you can literally walk back to McMurdo. And so it had, food, extra clothing, some fuel, pee bottles because of the Antarctic Treaty. You're not allowed to just pee on the snow. And so it was interesting to have that with you at all times and just think through your worst case scenario. So it's just a complete different mindset. In terms of whether that's necessary to do spacesuit operations, it depends. I think if we're looking more at the engineering side of things, I don't think it's necessary to go down to Antarctica. I think there are cheaper ways to test out the engineering side of things and the general operation, movement, and how different environments will interact with the suit. However, if you're trying to get the full experience, including the mental strain as well as the physical strain and understanding that overall fatigue and how the spacesuit design can impact or exacerbate any fatigue that's experienced in that harsh environment, then yeah, absolutely. I think Antarctica would do that. Or a very, very long duration isolated experience, somewhere in the continental US.
Maybe North Dakota.
Yeah, exactly. Exactly.
Especially in the winter, right?
Well, let me mention something funny. When we went to Antarctica, we prepared the suit with glove heaters and a lot of different stuff, and we tested it in North Dakota at minus 40 something, which is the temperature that we have in January or so. And then we went to Antarctica in the summer, and the temperature was minus 3, minus 5. So it was way more comfortable in Antarctica than in North Dakota. So all our heaters and everything else were just turned it off because they were not necessary. So, yeah.
Being from Minnesota myself, which has some similar winters, I
Yes.
100% believe you. I
Hmm.
remember times I'd look at the temperature in the Minnesota winter and I'd be like, gosh, it's warmer on Mars right now, I think. Like this is wild.
Yeah.
Um, so this does unfortunately conclude our fantastic conversation today. Thank you so much, Dr. De Leon and Dr. Matula, for joining us and sharing your really unique perspectives and significant backgrounds in this area. It's been extremely valuable to our research community and to all of us here in attendance today. So thank you very much. As this is the end of our series, I do want to also offer a really special thank you to both Sam Shattuck and Jessica Busker York, who are organizing partners for this whole series from the Human Performance Collaborative. Sam and Jessica, you are such fantastic people to work with, and you have made this series possible and what it is. So thank you for all of your hard work. As I said, this is the last one. We are taking a break over the summer. So I hope everyone has a great summer. Go out, enjoy the beautiful weather, and definitely come back and join us again in September when we will be starting off the bioastronautics series again. You'll be hearing from us between now and then. Don't worry, we love to send you emails, so you'll definitely be hearing from us. We will be sending out an email following this event that has information about where you can find the recordings. We'll also include our fantastic speakers' emails. They've both given us permission to send that out and to share that. So if anyone has any questions that weren't addressed during this, you can always ask those again. And then, yes, please come back and join us again in the fall. And overall, thank you so much to everyone who has attended, who has participated, and who has had the audacity to think of really big topics in space and dream big about what it is that collectively we can do together in the future. All right. Have a great Friday and a great rest of your week.
Thanks, everybody. Bye-bye.
Thank you all. Thank you, Abby.
Bye-bye.